it's such a pleasure to be here and talk about embodiment, because as a roboticist, it's not easy to talk about embodiment with other roboticists, you might imagine. So let's start from the title. The title is What's Catching Your Eye? Why we look in places and why we look here and not here, and why we are attracted by different features of the visual scene. So that's my question. I started this question with my PhD, and I'm still trying to find out the reason why. Hopefully I will die before. So, yes, at the moment I'm the principal investigator of my project, Marie Curie project, at the CTU in Prague. But as you have seen, I wandered around a little bit, as a researcher should do. So let's start from here. That's the dream, right? It's a dream for me, it's a dream for everyone. I take the call, and my robot is cleaning and preparing a cup of tea for me, right? This is what we want. But then something is going on in the scene, right? Let's keep it here, put it in a drawer, and think about it later. So we want this. But how do we want this? We want this with an unconstrained environment. We want this with low power consumption, which is a thing that in the deep learning community is not super thought at the moment, and low latency. The latency is actually another good point for reacting very fast to the things that are moving and changing, right, in the scene. So, as I said before, all of these constraints that I set here, if you think about it for a second, someone has already done it, right? Has already solved this problem. It's nature throughout evolution. Look at this. That's, apart from being a cutie, it's an easy task for a cat. Is it for robots? Do we have robots doing this easily in our places, in our homes? I'm not saying Atlas doing the backflip with 300,000 takes with video camera and taking just a good one. I'm saying robots in our place doing this. That's not easy. It's really difficult to explain how to do this. Same thing here. The dog clearly understands, I give you the paw and you give me food. That's not easy again, because you're not only thinking about, he understands and does some Pavlov to understand like when you give me a treat is because I gave you a paw, but he's also balancing the weight, he's also standing there, he's understanding lots of other things at the same time, right? Let's think of this cutie. This is, I don't have kids, but I think it's 1 year old, like something like that. But it's already interacting with the toy, right? And think about me now. I'm talking to you, I'm standing and walking and trying to make the presentation fun, because otherwise we will not get to the end. And I'm doing all of this with 20 watts. That's insane, right? If you think about a normal computer, a normal GPU can get up to 200 watts. Just maybe to do object recognition. I'm standing, moving, talking, thinking, all of this in 20 watts. So I think I don't have to explain and convince you why I take inspiration from nature, because it explains itself. Okay, let's get back to the question that I had at the start. Is this going to, yes, probably. It's okay. It's okay. Maybe I can use the microphone. Maybe I can use also. Because it's letting me. Might be better. Can you, no? Can you hear? Yeah. Can you hear me? Okay. Whilst I'm filtering the noise. Okay. So let's get back to the problem, okay? I said that the problem is an unconstrained environment and lots of other things, right? Which we are used to do without even thinking about it. But then, okay, here something is happening. How do I tell the robot, forget about everything else, the cat is about to burn to hell. How do I prioritize? Then the question becomes, how do I define attention, visual attention? Okay, so I need to catch that there is a candle that is moving and falling down. So let's stay here for a second. Now I'm going to play a video. It will be played twice. I'm not going to spoiler anything. You just look at it, and then you tell me if you found something, if you caught something. Just look at it. Okay, did you get anything? Just tell me anything, anything. Yes?
He looked at the phone when he heard the sound in his phone.
Say it again, sorry.
Like he looked at the phone automatically when he heard the ringing.
Yeah, good. Yeah, other things? Just anything. It's not complex, like I'm not looking for, solving the relativity. Just anything. Yeah? Strange phone, okay. Yeah?
The plumber tricked us and it's 2 different videos and it's something is different the second time. I don't know.
2 complete different people. Yeah, because I couldn't use the gorilla, everyone knows the gorilla passing by, so I needed to be creative. So, fine, 2 different people, right? But the interesting thing is that actually, I would say that each of you got it right, even though you said, all of you, different things. Why? Because what we do is that we focus on the informative information of the scene. We don't really care about all of the details. We couldn't process everything. So what we do is that focusing on the informative information. What does informative information means? Let's talk about it and let's see. Okay, so we are in 1967. This is Yarbus. Although I think I put every time my Italian pronunciation on it, but this is the guy. And he wanted to understand why we look in certain places and what we do with our eyes. How do we scan the scene? So, if someone guesses what this is. Yeah, do you know it? You said you know?
Fixing your hand in a very defined position.
And?
Yeah, then you track where the eyeballs are moving.
Yes. This is an eye tracker, guys, from 1967. Imagine being the subject. I was like, I don't mind about science. Just go on yourself. So, actually, he found some subjects. He found it. And these very brave people looked at different scenes, right? So, this is a scan path. A scan path is a recording of the eyes moving, scanning the scene. So, have a look at here. We basically go from one head to another head. So what we do here, easy, is nosing. Are they fighting? Are they saying something interesting? We're curious, right? What we do here, easy. Again, triangulation. Do I know this person? Do I not know it? What do we do here is foliage, foliage, foliage. Oh, there's a bear. I might need to run very fast. So you can intuitively understand me when I say that we have the most informative information, but measure that is not easy. Trying to understand what does that mean, it's not easy, okay? Let's go on, because this is just the intro. So we have an image, we have the scan path, and then we have the saliency map.
The saliency map is telling us the places where we fixated the most. So potentially the points of interest for our eyes. Then in 1998, these three people, E.T., Christoph Koch, and Ernest Niebuhr, tried to say, okay, can we model this? Can we create an algorithm that is able to give us some saliency map as outcome? And then I can use it in robotics and I can do lots of other things, right? So what they have done was just doing feature extraction. So they extracted the colors, they extracted information of intensity, and they extracted different orientations. Then they do different scales to be scale invariant, and they sum up. They get the winner take all, one single salient point. So basically what they do is trying to understand a bottom-up feature extraction from the scene, which is very cool. But feature extraction is not enough. How do I understand that all of these lines are a single thingy? How do I understand, how do I perceive this as an entire plant? That's not easy, right? So how do we understand the items around us? Gestalt. So let's start from 1950. We have Gestalt principles, right? And all of these principles give us the information on how we perceptually group the visual information. There's different ways with closure, similarity, figure ground organization, and proximity. Let's start from here. If I ask you, what's this? For sure, you will tell me that's a square. But because your brain is so smart that fills all of the gaps and say, okay, is there anything I can classify? Yeah, that's a square. What we do here instead is grouping circles with circles and triangles with triangles, because we group for similarity. Same thing here for the proximity. And this is just our way of distinguishing the foreground from the background. So these are rules that help us trying to understand how we perceptually group the information of the visual scene. So, shift in time, you can get it there, is 2000. Is 2000, and Zhu et al. Look at some cells. They found some cells in V2, so in the secondary visual cortex. They look at the cells, basically looking at these scenarios as A, B, D, C, and D, where you have a background, regardless the color, inversion, and then you have a foreground. The cell is that black thingy there. So, how the cell is able to respond only if the object is on the left. How is happening? Why is not responding here? This is spurious activity. How does it know where the object is, if it's on the left or the right? That's kind of creepy. So let's have a look at the cell itself. And let's imagine the problem of the closure. So we have some corners facing towards each other that might resemble an object. What if the cell has this shape? So what if it's an banana filter or an half moon filter? What if, as is really common in cortex layer, we have a group of cells looking at the same point with different orientations? Then we get that that is an object, or something that belongs to the same solid thing that is moving, which is impressive. So they call them border ownership cells because they are giving you the ownership of that edge, of that border. And this is a proto-object, is not an object because it's an object to be. We are not recognizing the object at this level or stage of the visual part. We are just saying, okay, there might be something that might be an object. And this is the von Mises filter, which is the filter that we have used from 2014 to model these cells. So, this is exactly the same model I was showing you before, where we have intensity, color, opponency, and orientation, but here we have now border ownership and grouping pyramid. This means that we have this filter convolved with different orientations, and then you sum up the information of the different orientation you group, you pool, as is often done by the cortex. Okay, guys, we got to the start of my PhD. It's going to be a long journey, stay with me. This is EACVA. I don't know if you know, EACVA is the, there is a debate, but it's one of the first humanoid robots, and it has been built in IIT, weirdly in Italy, from the Italian Institute of Technology. It's part of a big grant, and you see that it has the face of a kid because it's trying to not scare people, but it's basically the most complex humanoid robot present at the moment on Earth, because it has, first of all, 5 fingers, which is very difficult for grasping if you work with grasping, and lots of other joints, and degrees of freedom is really complex. Okay, so question is now, how do we perceive? But before saying how do we perceive, how does a robot perceive? So, of course, we know that we have the cameras, the eyes, then we have the ears, then we have all of the touch, the sensor information of the robot. So I would say that yes, we do in robotic have lots of material, lots of body to work with. It's a matter of trying to understand how to use that body and what to do with it. So of course we have all of these sensors on the robot. But the question is, okay, but us, how do we perceive? So if we imagine that we have a single cell here, let's call it, so it's called the receptive field. Let's call it a little patch in your skin that is able to respond when it's touched, so when it's stimulated, okay? So let's imagine that it becomes yellow when it's touched, okay? So now let's think that this thing will be touched in time depending on how much I do this, right? Therefore, all of these are events in time. So let's stay here for a second. We call these events, but the point is that this is sensibly different from what's going on in a robot. The robot is checking for all of the sensors, all of them periodically. Can you imagine how this is not efficient? We in nature are very efficient because it's the other way around. It's the sensor telling the brain something happened. Instead, what we do is let's check all of the sensor every clock to see if something changed. It's really, I don't want to say too much loud, but it's stupid, right? We are way more efficient. So this is what's happening, right? We are checking every clock all of the sensors. We are checking just the sensor that changed. It's the sensor telling us what's going on. Okay, this is why we call this, in my specific laboratory where I had done the PhD, the neuromorphic EACVA. We say it also for another reason. Is anyone familiar with neuromorphic vision, neuromorphic cameras? None of you? Yes, something, okay. So let's say for the others, how does a neuromorphic camera work? Okay, so what we do when we record the video is basically a sequence of images, right? Detecting the light, and it's getting this every chunk of time, right, is periodic. But the point is that if I have a bottle and the bottle is just static, nothing is happening, what you get out, it's a sequence of the same exact images over and over, redundant information that you might not care, but computationally, a person working with like terabytes of data, we care, we do. But most importantly, if it's moving way faster than in between two frames, you're completely losing the information at all. So what if, instead of sampling in time, we sample by the y-axis? This means that you have a grid of sensors, and if the light in that specific sensor changed over a certain threshold, then we make the sensor telling us that something changed. Then this is effective, right? And most importantly, we get nothing if the bottle is static, and we get all of the information if the bottle is moving. We call these events, as I was saying before. And each event in the neuromorphic event-based cameras is giving you the information of X, Y, timestamp, time, often again, completely lost in the deep learning community, and the polarity, which is just telling you if there was an increment or a decrement in light. So this is what you see with the neuromorphic cameras, and they're bioinspired because they're trying to mimic the first part of the retina. If you read the paper, they said until the magnon and parvo cells, no way. First layer of the retina. This came out many years ago, but the point is, which I want to play it again. So this is what's happening in your retina. You have these receptive fields that are reacting to light in time. So it's asynchronous. You have the information in time asynchronously, which is a completely changed paradigm shift, right? So I could say that my algorithms now need to be embodied with the hardware that I have, because I can't use just any other algorithm that I was using before with frames, but I need to follow what the hardware is asking me to do. Okay, so at the end, we have EACVA. We know that I was working on attention. We know that we have event-based cameras. And then what I wanted for me was the EACVA to be able to detect attention cues from intensity, from the depth, because I want the robot to grasp things that are closer to the robot, and from motion, because motion is inherently interesting. So basically, this is what I've done, or I managed to do during my PhD. So we have different channels of information, intensity, depth, and motion, as I was saying. And we have the proto-object model that you can see here in the depth and the intensity, but not here. Why? Because if now I get crazy and I throw the microphone to some of you, you don't really care to recognize if it's a microphone, you just move. So motion is inherently interesting without detecting if it's an object or recognizing what it is in that specific moment. So let's go on. Well, how much? Yes. Okay. So I started from the RGB model, and of course I had to change everything, right? Because, I mean, I had event-based cameras and I had to work with them, right? But the RGB model is doing something that is interesting. They're performing a center surround layer, which is basically a difference of Gaussians, which if you talk to a computer vision person, they will tell you, of course, they are doing edge mapping. So what they were doing here is just getting the edges of the scene. And then they also try to understand the polarity, so dark over light and light over dark, the contrast. But with the neuromorphic cameras, I get it all. I do not need any of that because the contrast, the light change happens only at the edges of the objects moving. So I already have an edge map and I already have the information of polarity because the sensor itself is telling me if the light was increased or decreased in that specific grid, part of the grid. So I could get rid in one go of 2 processing layers, and that was actually cool. We have done the model the same, and then we performed some experiments, which these were my first experiments of the PhD. I'm not super happy about it now, but let's get on to it. So basically, here we have 2 patterns that are really important for saliency-based attention. One is proto-object and one is non-proto-object. Do you remember when I talked to you about the squares, the 4 corners facing towards each other? Well, this is a proto-object, right? Because of the Gestalt laws that we put in our attentional model. So as you can see here, we have a strong response inside the 4 corners facing towards each other. And of course, we have some spurious response. Why? Because we are not perfect. And if you do bioinspired algorithms, they're not going to be perfect. So this is spurious response from the model. So important to say that the model was running on a classic GPU for 100 milliseconds, which is good-ish if you work in neuromorphic, okay? So the point is, this is the RGB model, this is our response. You can immediately say that our response is much more localized because what I'm doing is trying to mimic that part of the brain with a spiky neural network. So these are my neurons spiking, right? I don't perform, like here we perform a classical convolution, but then we will talk about other things. Okay, then we try to understand the depth, as I was saying. And I want to show you the full thing, because I think it's nice to see. We skip the model. We don't care. Yes. Okay, let's stay here for a second. So what we were looking at before is that I feed the model with the intensity, right? So with the events from the camera. So I get some attention based on intensity. So now what we do is a disparity extractor, which was a stereo-based, event-driven disparity extraction. Do never do something like this because I lost 2 years of my life. It's super difficult and complex because the laws of continuity and uniqueness are a bit crazy because you're working with dots, you're working with events. So what you have out of it is a disparity map and information of the things and how these things are close to us or not. So I am feeding that to the proto-object model. So what am I doing here? I'm basically giving attention to the closest object from the robot. So there is a significant difference between the 2 models. So if you look at here, do we see? Yeah. So here there is the RGB video. These are events, rectified stereo events. Here we have the disparity map. Here we have the attention from the intensity channel. And this is the attention from the disparity channel. It's very clear if I let it go. Yes. It's very clear that in one case, I'm looking at one object and I'm very stable. But what if I put another object? Then the attention, which is a red dot, is moving from one object to another one, right? But what if I put the disparity information? I'm basically telling the robot, look, just fix your attention on the closest proto-object that you find. And it's doing it, because it's quite robust. So basically, we have given a task. So Yes, the model perform because what we have, again, are results that we compare. So the model, I don't want to say that I don't like my results, because I do like them, but it's difficult to explain this thinking specifically. So my ground truth are real human subjects looking around. Of course, it's difficult to understand the differences between my simple bottom-up model and how complex a human being can be, right? Because you look in places not only because of bottom-up features, but also because maybe the day before you were, moving somewhere, you were preparing boxes, and then your cognitive bias is fixating on boxes, and I cannot know that, and it cannot be validated on my model. So this validation is still very good in terms of saliency bottom-up models of validation, but of course we will never reach one. Okay, so that's my point. So other point, 170 milliseconds again in GPU. Why do I talk about GPU? This was really Italian accent. Why do I talk about a GPU? Because actually what I do is also computing neuromorphic. So my pipelines, or I try to create architectures that are end-to-end spiking based, so end-to-end neuromorphic. So what you see here is Spinnaker, beautiful old Spinnaker, came out from the Human Brain Project, and it's 48 ARM cores giving you and emulating neurons for you digitally. So this is the word of the digital. You can emulate neurons also on the circuit with circuits. It's way more difficult because, of course, it's less reliable, but you can. So this is Spinnaker, and then the same attention model has been done with the neuromorphic platform, which, let's forget for a second about the specifics of the model. Of course, everything changed here, right? Because I'm not doing a classical convolution. I really do have neurons. I really do have the time. I really do spatiotemporal integration and spatiotemporal with time information, which is, of course, the benefit of using spiking neural network. But the point here, it's this. That's why I said 100 milliseconds is because I'm used to this. So I give the information of where an object might be in 16 milliseconds, which in robotics, this feels amazing. Yes, this is the bad part. I need 6 of these thingies, which are big like this, next to the robot. So it's unmanageable. But the scalability problem is a known problem for our community, and we are trying to understand how to squeeze other transistors, but it's not that easy. Okay, so we got basically to the end of my PhD, right? And then we have all of these amazing ways of getting the saliency map. Is there any saliency map in the brain? No. Spoiler. But is not everything lost. So, point being is, what we are used to think is that we look around with frames. We think that we look around and we collect videos. It's not working like that. We don't have a frame that is given to the retina and then given to the V1. It doesn't work like that. Not at all. There's not a mini version of you right now in my retina. It's not happening. What it happens is this. We perform actions in the environment depending on changes into the external world. We don't have a static frame. passed by like a fiction to the V1, then is it the active interaction with the word that is the response for robotics? Maybe. Then for me, embodiment for me, or what I'm trying to push to my community, embodiment refers to the concept of experiencing the word with a specific body, right? If you just cut out the brain of a crocodile and you put it inside the body of a giraffe, that's not gonna work. So if you do an AI algorithm, deep learning, whatever, how many layers you use, algorithm that is working on one specific spot robot, for example, a dog, and you try to put it on Atlas, whatever, another humanoid robot, and you tell me that that's embodiment, because you need to follow the body in this sense. In one case, we have 4 legs. In another case, we have a robot standing and walking, completely different. The algorithm needs to change. So what I'm trying to propose now, or the grant that I wrote, is that we have the standard view, fine. What I want to work on is the sensory motor view. So this means that I want to connect the movements that we do around with the spatial changes that happen when we look around. If you associate that, you have some sort of relationship between your actions and the external changes. So the environment is shaping what I do and vice versa, right? So if I do this, then I might have a sequence of sensorial information and actions, and those sequences maybe can tell me that a cup is a cup. So what I'm trying to say is that we might not even need frames at all to recognize objects. Maybe it's not needed to train on a huge data set. Maybe what we need to do is looking there for specific points and associate those parts of the image together, that maybe that is a solid object. So for me, perception is not an isolated processing step, but searches for relationship between actions and results changing. So this is the Marie Curie project that I wrote, and luckily I won. And what I'm trying to do is trying to understand what's happening in the developmental learning of infants when we look at objects, and indeed we get an object and we move it to remove occlusion. We move it with the eyes, and we look around and we manipulate with our hands. So in other words, I'm also saying that vision is exploratory as much as manipulation, but we are not used to think about that this way. And what I'm trying to do is doing this association of joints, position of the pan and tilt, and the external changes that is happening in my retina. So this is one thing that I want to show you, which is basically the start of my model being put on a robot. It happened in Telluride. Telluride is the neuromorphic workshop, engineering workshop in Telluride in Colorado, where luckily I was one of the group leader, and I will be also this year. And basically the robot is moving around based on the attention model. And one thing that I didn't tell you is that there's no way, nowhere in my GitHub repository or in any paper that I wrote, learning. All of my methods work without the need of training and learning, but just using the structure or how I build my network in a specific way. So this resulted in some results. So this video comes from previous Saturday, where I think I got something important here with the usage of these event-driven cameras, but I'm not bold enough to tell you now, but in a week I think I will put it on archive. Point being is that these cameras probably are not meant to be moved around because they are bio-inspired. They take inspiration from our eyes. Our eyes do not move like this, right? We tremor in fixational points and we saccade. But during the saccade, mostly happens saccadic suppression. So it's important to understand, this is pure embodiment, right? Because it's the camera itself that tells me that it would work properly only if I know how to make it use, because our eyes are working like this. And the camera takes inspiration from the eyes. So point being is that this pipeline wasn't working very well because I put my camera on a pan and tilt unit. And then I was getting the information of the attention in 10 milliseconds, okay? Everything. I was segmenting motion and getting the attention in 10 milliseconds. But the problem is that the pan and tilt unit was moving to all of the places, right? Because I wasn't adding this part, the microsaccades, the fixational points, like the fixational movements that we do after the saccade. And this explained everything else. So if you look at it now, I see, and I moved, and I put the interesting point into the center of the camera, as we do. So I am trying to foveate, I'm foveating around. But the point here is that adding fixational movements make me never blind, which is indeed supported by literature. We have these microsaccadic movements because otherwise the visual scene would fade away because you cannot get the contrast. So yeah, I'm very happy about this. I not work only on attention. This is indeed what I have done with Liat in 2000-something. We don't remember, both of us. But we worked trying to understand how a robot can reproduce brush strokes. And the good part of it is that even because it's end-to-end neuromorphic, now you understand why I'm saying that my models are not precise as we are. So the beauty of this work is that is reproducing brushstrokes with the same amount of variety that you would have from a real person. So we tried to make it a little bit more human-like in this sense. This is just another paper that is working on attention. I added some recurrence here and is basically giving me a much better information of where an object here. This is coastline detection, and what is good of this publication again is that there's no learning. I'm giving you the coastline. Let me show you how I give you the coastline. So it's a spiking neural network, and it's giving you the coastline here. So it's detecting, so I have my neurons that are spiking when the near shore is happening. Point, I give you the information for 20 milliseconds with 0.3 milliwatts, which is insanely good, right? And of course, I had a reviewer to, oh, why you don't compare with an RGB pipeline? I mean, man, I'm giving you the coastline detection even before a frame is even generated. So I don't know what to do about that. And thank you for being with me all along this talk. So these are the people I worked with. I'm very lucky to still work with Ernest Niebuhr, which is one of the guys that in 1998 have done the visual attention model first. This is my professor in Prague, Alexander Gijanov, Chiara Bartolozzi, my boss in IIT, Dylan Muir from Sinsens that is producing neuromorphic hardware, and Yulia Sandamieskaya, she's in Zurich working in neuromorphic too. Then this is a project that I have from 1 year. I'm the co-founder of the Brains&Machines podcast. It's me, Dr. Sunny Baines is a professor at the University College London, and Professor Ralph Etienne Cummings from Johns Hopkins University. And there was a person asking for Rodney Brooks. Was it you? Yeah. Go here. There is one of the latest episodes is we interviewed Rodney Brooks, and it's talking about embodiment beautifully. So it would be nice and interesting for you, I think. This is Telluride Neuromorphic Workshop, with which I collaborate every year. Open Neuromorphic, which is another association where I'm the editor of it, same thing for NeuroPAC, and this is my new podcast, which is Sotto Soglia, and is talking less about neuromorphic, but more about how difficult it is to be a researcher in this academic life. And thank you so much.
Thank you. Thank you, Giulia. Just stay here with me because I have a feeling we're going to have a lot of questions for you here. So any questions already set up on the view? They're tired. Okay. It's need time to process, but here, Frederic, I'm going to give you the microphone.
Very impressive. I have a computer vision background, so I can see all the nice work that's going on. I'll mention a few points, but you haven't mentioned touch, and I was wondering if that's a future direction for you to integrate with vision and maybe sound and movement. And you had some talk at the beginning on perception. So we saw, for example, the Canizza triangle. And so I was wondering, the focus on movement and contrast, what does it give us to understand visual illusions of that type? Because they're, to me at least, they're a sort of static type of phenomenon. So just question mark. And is there any place in your thinking or objectives for representations? So by that I mean a concept of what's essential to know what a square means, or a triangle, or your bottle, or etc. And how do you, would you link that, or would you try to explain with the neuromorphic generation that we have now, can we go as far as understanding dreams when the eyes is not looking?
Okay, let's start from the touch. So I think you can hear me clearly. Yes. So the touch is a new huge point as you. Thank you. So indeed, the touch is really interesting, and in my laboratory in IIT, we are already doing it. I say we are because I'm still collaborating, so we are already doing it, and we already have a neuromorphic touch. Indeed, I'd like to get to the visual-tactile receptive fields that we have, because of course I can feel here that I'm touching because of my skin here and receptive field, but I know I will be feeling the touch if I put my finger here, because we have this visual-tactile receptive field. So for me, it would be super interesting to add this touch information. At the moment, I don't like the Marie Curie is super nice, but it doesn't give you money for a PhD student. So I really would like to have a PhD student and start exploring something and buy more. Hopefully, this will happen soon. So definitely that would be one of the directions, because then you can refine both touch with vision and vision with touch. So definitely, I'm super interested about that. And on this regard, I'm trying to explore game modulation. When I was at the King's College of London, I was working with Michael Spratting, which is very good in predictive coding. And they came out also with gain modulation, also to try to understand and change reference frame to move from the touch and associate it with the information of the vision. Or this happens also in V6 for the grid cells. Because basically I know that you are there even if I move my head, and even if I move my eyes, I still know that you are there. So definitely this would be other two directions that I will explore. Second question, what was it?
It was more about a phenomena that seems to happen in static sense. So, for example, the chemical.
Right, so that for me just represents a triangle, not the illusion. It would be extremely interesting trying to understand all of the different problems that we face when we cannot recognize something in front of us, then the illusion happens. Most of the time it happens because we have lateral inhibition in our eyes that is basically you know that when you look at like spatial frequency gratings, if the frequency is so high, then you start filling up the white part as well. And that is because lateral inhibition that we have in the retina. I am trying, we are developing a library in Python, basically replicating all of the layers of the retina, so I'm sure that those illusions will come out. But another really interesting thing, if I'm talking too much, you just stop me. Another interesting thing is that I came out that I met a guy that is working in schizophrenia. And it happened that the receptive field size of these people, of people with schizophrenia, they do not shrink and enlarge with circadian rhythm, right? So with the day and the night. And this affects the visual perception of them. So indeed, it seems that we cannot find any schizophrenic patient born blind. So this is like a huge thing, because this means that maybe we can help them with this mechanism. So it's not about trying to get the illusion part of the visual scene. It's about just about grouping edges with borders and grouping them together to try to understand if there is a solid thing somewhere. So it's just trying to get proto-objects. Then there was a third question, right?
Yeah, the third one, I guess, tough one, is there
Dreams.
representation?
For the dreams.
Means, and then how with the neuromorphic approach,
Yeah.
how do we get to the point where we can dream? Because we create visual sensations in
Okay. Let me. So, one part is basically what I'm doing in my Marie Curie, which is I'm trying to recognize objects not because of frame, but because I associate parts of the, let's imagine we have a box here, right? So I associated that this corner here, it's next to this, it's next to this, right? And then I fuse them together in time. Indeed, a good thing to do would be contrastive learning through time, which is associating different features in time, and you get that that's might be a solid thing. So I gave a talk at IBM, and it happened that they have done it. But at least I know that it's working. So I am going in this direction, and I'm trying to associate a label from a sequence of movements and these little patterns, okay? So this gives you lots of flexibility because you are not learning based on a bounding box over the objects so that you see the full object, and therefore you need to mask for occlusions, getting all of the clutter out and generalize for lights and so on and so forth. You are getting this spatial edges together in time. So we are way more flexible to detect objects, just depending on the time of the sequence that we record. This might indeed, probably, become the start of recreating another object in dreams, maybe? I don't know, I'm just thinking as I thought. But if you look at Telluride neuromorphic workshop, there was the first, previous year, the first group that was working on language and thoughts. And we got very, very close to that. So if you look at the website, there's some work from them, and they're working on thoughts and how to understand how the neurons talk to each other, also during thoughts and dreams. Yeah. Thank you.
Any further questions?
Thank you. I would not be asking a question if somebody else was asking one. I would have enjoyed learning more from your answers to other people. Basically, everything I know about this topic is what I've been able to understand of your talk just now. So, you know, which is, I think, a lot, but other than that, nothing. And so it's just a question for clarification. You talked about what happens when you integrated into your model or your calculations the microsaccades, and how that made a huge difference in the outcome. And I didn't understand that step, and if you could just say a little bit more about what that is, it seems like it would help me understand a little bit more.
So this is a really new point, because if I got this right, I'm basically telling the community how to use these cameras. So don't take everything I say, but yeah, you know, I put my hands. So the point is that when you move your eyes, you saccade, right? And saccade is just moving from one object, one point of interest to another point of interest. Another thing to know is, why do we do this? We do this because our retina has a different non-uniform size of the receptive fields. This means that in the periphery, everything is blurred, okay? So if you look here, you don't see very clearly Liat in this very moment, right? Because it's blurred, it's in your periphery. So this means that your eye has the center highly resoluted. Therefore, if you want to see Liat, the only way is to move your eyes from me to her. That's a saccade. We do that to recognize better. So, point being is, okay, your retina is giving you information of light change in time. If I am here, static, I don't move, there's no change. So the information of me would fade away in your eyes. In order to avoid this, the eyes perform fixational movements. Whether it's a microsaccade, whether it's a drift, it's just imagining a tremor, okay? It's doing this because otherwise it wouldn't see anything. I don't know if, I'm gonna go with a quote of Jurassic Park, but it's very scientific. But in Jurassic Park, he's saying, if you don't move, it's not seeing you, the dinosaur. It's because they didn't have this tremor. So it's fading completely, and the only way to see is that they needed to move around, okay? We solved this problem, adding this tremor. So we tremor, and we then have time to understand what's going on in the scene. We catch the next salient point, and we go there, okay? This happens bottom up or with some cognitive bias, if I tell you focus and track Liat wherever she goes, okay? But that's the point. Yeah. Was he?
Just the way that you integrated that, I mean, maybe that's way too technical, but so that made a huge difference in the output.
A huge difference, because our problem with these cameras is that either you don't see anything unless something changes in your visual field, or when you move, you get the events from objects moving in the scene, but also because you are moving the camera. So how do you distinguish the events that are coming from objects from the events that are coming from your movements? And I'm going to tell you another more thing. We do not have proprioception at the level of the retina. Proprioception happens later. So how the retina solved this? I had this question in mind in 2019, and I saw that there was some biologists proposing a model of the amacrine cells, which is basically the third layer of the retina. You have bipolar, then the bipolar is talking to the ganglion, but in between you have horizontal cells and amacrine cells. These amacrine cells are spatiotemporally integrating the information. That's why they're called horizontal. And what they do is that they compare local motion. They look for patterns of local motion there. If you apply that, magically, you are able to see only things that are moving, even though you are moving. But the model, it's terrible if you move the camera fast like this. It works only if the camera moves this way. And therefore, somehow, I mean, this is linked with the microsaccades. And the cameras that I have are bioinspired. So somehow I was like, you know, yeah, it works. Yeah, because like I proved myself the need for fixational movements. Thank you.
Any further question? Yes.
I just have a silly question. It's about the crocodile brain in the giraffe body. Oh, yeah. I'm sad I didn't see it. So you said, yes, this isn't embodiment, right? And I totally get that. But, you know, especially in biological organisms, there's this aspects of neuroplasticity. And, I mean, let's say that the crocodile's brain was living in the giraffe's body for quite some time. I mean, I imagine at first it would fall over and not be able to eat anything, and but wouldn't it learn over time? And I just wondered if you could talk about how you maybe see embodiment as a process rather than in that example it seems more like an event.
It starts from a frustration point of view. So let me tell you. Google came out with the paper having the same algorithm put in different robots, and the title is embodiment robotics, okay? Which is the opposite of robotics, because you don't want the same algorithm from different robots. You want the algorithm to follow the robot that follows the algorithm, okay? So it starts from this frustration, so that's why I say this. Because it's very difficult for pure roboticists to understand this information, like that, no, it's okay, Kalman filter, they work this way, and it's really difficult to get the embodiment part as a way to describe a robot. Definitely, if you learn, it depends. If you put, I don't know, it depends on the species, right? If you put, I don't know, a brain of a crocodile in a wheel, I mean, that might be difficult even learning. It will never get there, okay? I mean, indeed, this heart transplant, right? But would you bet about your brain transplant? I mean, if I tell you, you know what, just transplant your brain with mine, it's gonna work. That's scary. So for sure we are gonna learn, but I don't know how much you can learn from what have been already learned. I mean, your muscle already knows some things, right? You can adapt slightly, and this is true because we have prostheses, right, that are moving, and your brain is actively trying to repopulate and recreate the connections. But it's difficult, it's really difficult to give you a response that makes sense right now, because I think we are so far away that for now I prefer to say that it's really difficult to think that you put just a brain there and it's working instantaneously. You know, it would definitely learn, but difficult. Yeah. Thank you.
Frederick, you wanted to have another question?
I was just thinking, what do you call the brain? Because, for example, here we're talking about the retinal, but usually when we see a picture of the brain, like the neck, there's no retina. Where do you cut the nerves that go to the brain? Which part?
I don't cut anything. I don't cut. I don't cut. That's the point of having mind and body, right?
Your example.
Ooh, sorry.
Your example, would you say, when you say the brain of the crocodile, is it what we draw as a brain, or is it the entire nervous system? If not, where do you cut?
Exactly. No. I totally understand. I don't cut. First of all, it's at least the entire nervous system, right? Because otherwise, but the nervous system is talking to your legs, to your arms, right? So you shouldn't cut. That's why I really don't like the approach of just getting the same algorithm in different robots. It doesn't make any sense from the embodiment point of view. Yeah, I agree.
Does that mean that you would never consider mass production of robots?
Mass production of specific robots. Which is annoying, because I know, like, it might be nice to have everything in one go, right? Like, for example, our phone can do lots of things, right? So what I'm proposing is, okay, we have the dishwasher to wash the dishes, we have the, whatever, the coffee machine to do the coffee. I'm proposing this. But would you imagine a single thing doing it all? I mean, we need to start from somewhere, and you need to start from robots that functions. I mean, the best, like now we are scared about, robots stealing our job. Geez, the only thing that is working is the Roomba. There's nothing else working. There's nothing, no, because we are scared, like these robots will do, no, they barely follow a task if you give it to it, and very specific. It's not easy, because they still don't know how to jump, how to climb stairs. It's really difficult. So that's not the problem from today. So for today, the problem is trying to understand what to do. Like, can we get something that is working first? Which is basically what Rodney Brooks is saying, right? So don't take credit for everything, but is saying this: let's start from scratch. Let's start from one specific thing at a time. Once we have all of this working, then we move and we integrate things. Because do you imagine now a robot like Roomba walking, talking to you, and I mean, it's not going to happen. There's lots of time. It will need to take time, so I think, hopefully, so that they don't lose the job.
Okay, yeah, thank you, Giulia. I would like to maybe have one kind of a question to try to bring Yvonne's topics and your topics together, because it was something that kind of came up in both of the talks, and that was about adaptivity versus deterministic processes. And the way that I think both of you referred into the more common technology being used, it is about the deterministic process being used, and what you kind of presented with the neuromorphic technology is the ability to always adapt to ever-changing reality. And I wonder if it's much more suitable, or like to our human-like of thinking, being adaptive. And I think specifically in the round that we are here talking about creativity, creative work, painting, which you have to evaluate yourself, your step, and therefore as well the end result. You don't really know how the end result is going to look like. You keep adapting your body, your perception. And we are trying to use right now robotics to do this kind of a creative work. But I keep wondering, and I had this question when we worked together in Zurich a couple of years ago, why we don't see more of this kind of a technology, the neuromorphic technology, in robotics, in more common use, and how do you see it being integrated outside of research and actually being used by artists or normal even market?
We're trying, but it's so difficult. Yeah, because, like you have, when you talk to investor, for what is good for? I mean, can you ask the brain for what is good for? I don't know, for everything. It's computing in a different way. So Why we don't see more of neuromorphic? First of all, it's complex, because you need to have a strong neuroscience background behind, or otherwise you use it as you would use a classical deep learning network, but then you're not really using the time scales adaptability that we can have. And that's the first part. It's too complex, and people don't want to deal with complex things, not researchers. But imagine you have a company and you have 10 people in front of you. Would you ask them to learn about neuromorphic, or you would give them something that they have done at the university? Practical. You give them something that they already know how to use. And this is a complete shift of paradigm. Then you mentioned the adaptability. So another thing is that, of course, what I do is using or restructuring or modeling my architectures as the architectures of bioinspiration. This allows you to add on top even more adaptability and even more learning processes, because, of course, you can't be totally adaptable if you don't learn a little. Then you said another thing. Remind me. I'm lost. Creativity. So I see creativity even from us. If you do a painting and you do it 10 times, at some point that become network connections in your brain. You will do it with less creativity at each step, right? Because you are repeating over and over the same thing if you try to redo the same painting, right? So,
I had the same reaction.
no, I'm trying to understand. Yeah, it depends on your goal, right?
What you're talking about, you're describing a deterministic process trying to reach a kind of a vision of what you want to do.
Okay.
Like a creative and adaptive situation is more of an open-end, that you let the process lead you, and you always open a conversation. Like you're having a conversation with a person, and you don't try to convince the other person with your ideas. You actually exchange in order to learn something new, and the new is the result. And this is, for me, a creative process.
Because you made me think on how can I explain creativity with neurons? Because I think they're strongly linked with errors, mistakes that we make, right? Because I do a mistake and I try to adjust from it. That's creative.
But I also think that each mistake opens up a new set of pathways.
Exactly, yeah.
We don't try to
The more
correct
you
or
repeat
to
something,
Yeah.
the more you can get, because you're having, for me anyway, and I think
Yeah.
all the artists in the room can make a statement on this, but I think that the more you repeat it, the more you're doing it, the more you think of other ways that you might do it. So if I lie in bed at night, which I do often, thinking about things that I'm going to do creatively, that is a very deterministic process. And then once I get into the studio and start making it, everything explodes and the decision tree becomes far more complex.
Yeah, you see, my mind, because half of my brain, I'm an engineer. Half of my brain, I'm a dance teacher. I was a professional dancer, so I totally understand when you tell me if you think about it, you're not going to do it. And usually when I was dancing, the less you think about it and the more you feel and perceive, so everything is shifted to the perception of it. It's not thought. Is creative just perception? Sorry. We can close it here, please. Let me go because I'm scared.